Hey everyone, welcome back to our usual sequence on homework. Still staying strong on posting these videos. This one will be pretty quick. I just want to do a quick walkthrough of how we calculate absolute age when we're given percent amounts for things like parent isotopes and daughter isotopes. So just a quick review of some stuff we have talked about before. Sorry about that. Good old computer just doing whatever it wants to do. Couple things we talked about last week. Unconformities are gaps in the rock record. So angular unconformities are where you have tilted layers that sit below horizontal layers, indicating some sort of break in formation of these layers. Nonconformities are these boundaries between things like igneous or metamorphic, unlayered sequences, and more layered and even sequences of sedimentary rocks. And disconformities are gaps in the rock record that really can only be determined by absolute ages because the layers look sequential. So after that, we kind of got into absolute ages and we started talking about isotopes. So a small chem review. Isotopes are atoms of the same element with slightly different masses, and this is because of their neutrons. These different masses can lead to instability, specifically in the nuclei, and that leads to radioactive decay. We identified things like decay pairs that are parent isotopes, which decay into daughter isotopes, and they happen at this predictable rate. And we called this rate the half-life, which is the time it takes for half of the parent isotope to decay to the daughter isotope. So if you look at this handy dandy little chart I've given off to the left. If we've got our situation here at the newly formed crystal, we've got 100% of the parent isotope and no daughter isotopes in this first scenario. So you see all these little blue dots here. Those are all the parent isotopes. Okay, if we jump ahead to the 50% here, this one half-life has elapsed and we are sitting here at 50% parent and 50% daughter. Now, of that 50% parent, in one other half-life, that 50% will decay to 25%. And it says here 75% has decayed, leaving 25% of the parent remaining. And over time, those chunks keep decaying. So I want you to remember that we're not talking about 50% of the original sample. That only works at the very beginning. After one half-life, 50% of the original sample is decayed, and in one more half-life, 50% of what was remaining has decayed, which is essentially exponential decay. There's an equation for this, but we really don't have to worry about it too much because we have a handy chart here that just helps us walk through the relative percentages. So I wanted to show you one sample calculation for that and turn you loose to do your homework for the night. So let's say that we've got a solidified lava flow, and zircon mineral crystals were present in a sequence of rock layers. You take a sample of these zircon crystals and you count up the atoms of uranium-235 and lead-207 isotopes, and you reveal that 12.8% of the atoms were uranium-235 and 87.2% of them were lead-207. And we can answer a few different things for this. So ideally, what we want to know is what was the age of the sample, right? Sorry about that. So first of all, we have to identify which decay pair we're dealing with. It looks like we've got U-235 and lead-207. So if we go over here to our chart, this box is going to be the first place we look. We were using uranium-235 and lead-207, which has a half-life of 713 million years. It's useful for dating rocks that are older than 10 million years old. And we were given the relative percentages. So if we look over at our chart, just the actual graph, we've got 12.8% parent and about 87.2% daughter. So if you look here, it looks like we're dealing with this scenario right here. Close to it, right? 87.2 and 87.5 are pretty close. Which means if we're down to 12.8% parent here, close to it, we look like we've got about 3 half-lives elapsed. So if we want to know how many half-lives there have been, if we look down at our chart here, the little chart down here, we're looking at this case with this exact scenario. So there have been 3 half-lives elapsed. And if we want to know the absolute age of the sample, we just take 3, since there have been 3 half-lives elapsed, we just do 3 multiplied by the half-life, which was listed as 713 million years. Not too crazy, right? I don't even have a handy calculator handy. I'm just going to do this real quick. That is 21, people are probably screaming at me, 39 million years. which equates to 2.139 billion years. All right, nothing too crazy about that. So the relative age of our sample is 2.139 billion years old, which is within the realm of possibility here on Earth. Something we look for when we do these experiments is we kind of want to ask ourselves, does this number make sense? There's no reason to assume this number doesn't make sense, but had we gotten some sort of number that was, let's say, 8.8 billion years? Wow, goodness. This thing is just not doing it with me today. We'll have to go back into my slides. I'm sorry, guys. I think we'll survive, though. If we have something like 8.8 billion years... God, man, sorry. Anyway, just don't worry about the weirdness of the missing pictures. But if we have something like 8.8 billion years, that's probably not going to make too much sense because that's older than the age of the Earth. We might assume that something went wrong with our sampling, or we might assume that something went wrong with our experiment, and we might want to repeat it. Okay, so that is a pretty quick sample calculation to walk you through how you approach this kind of problem. Your homework tonight is to do the radioactive decay worksheet, and I will see everybody in class tomorrow. Thanks.